Physics students, good afternoon. Mr. Fugit here. In our video today, we're going to be solving through group problem number 4A, which covers over a scenario involving forces, friction, and a car trying to stop in a certain amount of distance. I'm not going to start by reading the entirety of the problem. Copies of the problem are located on Canvas under the Unit 4 page. I'm going to go ahead and start solving the problem, assuming you've read through the background and you have an idea of what's going on in our problem statement. So, the first thing that we're doing here, got a bit of an issue with our board. There we go. The first thing that we're going to do here is we're going to draw a picture of our scenario. According to the information that we are given, we have a car that is attempting to stop. So we would have something like this, roughly. This would be part number one. And we want to draw a picture of the situation and then label our directions. So we've got a car, like so. Oh, not my best car. There we go. We have a car that is moving forward, but there is an object, right? Our cuddly line of animals that we are trying to avoid. And there is a certain amount of space between us and the animals, about 46 meters. So there is a certain amount of space where our car is hopefully going to come to a stop. And we're told a few things about our car. It has a mass of 2,220 kilograms. Sorry, 2,200 kilograms, my apologies. We're also told the car is going at 60 miles an hour, approximately 26.8 meters per second. I'm going to go ahead and label that as our initial velocity, right? That is how fast we're traveling before we begin to brake and friction begins to work on our car. Okay? We are also told the coefficient of friction that describes the roughness between our tires and the road. And we're told that value is 0.7. Okay, so I've gone ahead and kind of drawn my picture. I've written in my values so I have an idea of what's going on. And as we've been dealing with in class, I'm going to call this direction to the right the positive x. And I'm going to refer to vertically upward as the positive y. Just so we're all on the same page with what we mean when we say something is in the positive x direction and what we mean when we say something is in the positive y direction. Okay? And that would cover over, not part one, excuse me. This is part A of our problem. Now, moving on to part B. Okay? Part B, there is a bit of a lengthy explanation here. Okay? One of the important parts that we want to see is this. We don't want to use a delta x of 46 meters to solve our problem because that will assume that we take this entire distance in order to stop. We don't actually know how much space it's going to take in order for us to stop. So what we want to do is we actually want to solve for a new delta x, the real delta x, and see how that compares to 46. Does it take us less than 46 meters to stop, at which point we would have enough space before we hit our animals? Or does it take us more than 46 meters to stop, at which point we would probably make contact and hit our animals? Who knows? So, what we're going to be doing here is we're going to be looking at the forces that are causing our car to slow down, namely a force of friction. So what I'm going to do, now that we have a picture, is I'm going to start by creating a free body diagram to represent the forces on our car. So here we go, our free body diagram. Typically, if we are on Earth, which we can assume that we are here, we're going to have a force of gravity. That is the earth pulling on the car. Because the car is also touching the road, there's going to be a normal force. The road is pushing the car up. Now, you might be tempted to draw a force going to the right. The reason that you might want to do that is because you're thinking the car is moving to the right, so something has to be pushing it to the right. But remember, Newton's first law states that an object that is already in motion has a tendency to continue in motion. So the car going forward is really a continuation of the motion it already has. That doesn't necessarily mean there's a force pushing it forward. Now, if we were hitting the gas pedal and the engine was thrusting our car forward, then there would be a force propelling the car forward. But here, once we begin to hit our brakes, there's not actually a force from the engines thrusting our car forward. There's actually, once we hit our brakes, there's only a force of friction. We would call this kinetic friction because it involves sliding between the tires and the road. But there's only a force of kinetic friction slowing our car down. So again, just because we're moving in the direction that is positive x, doesn't mean there's a force that direction. It just means our object will continue moving because of the trends described by Newton's first law, but that it will eventually come to a stop because of the force of friction. So we need to find what is our acceleration so that we can ultimately use a kinematic equation to solve for how far we travel. And the way that we're going to find that acceleration is by looking at the force that causes us to slow down. And primarily, that force is going to be our frictional force. So I'm going to write out Newton's second law. Now that we have a picture, I'm going to write out Newton's second law in the x direction. The sum of forces on our object is equal to the mass of that object multiplied by its acceleration. The reason that I'm going to look at the acceleration in the x direction is because our car is primarily moving in the x direction. Okay? So, this is moving us now into part C, looking at Newton's second law. So I would write in here the one force I have in the x direction is my force of friction. I'm going to refer to that as a negative force of friction because that force is directed in the negative x direction. So negative Fk equals mass times acceleration in the x. Now, if I wanted to, I could plug in my value for mass, but that's really not going to help me because I don't know my force of friction. However, we do have an equation for force of friction. You'll remember from class that is F sub k is equal to our coefficient multiplied by the normal force. Now, we don't actually know the normal force yet. We might have to use Newton's second law in the y direction to get there, but we do know our coefficient of friction. So once we find an equation with our normal force, we can use that to find our force of friction, plug that in here to get our acceleration value. So still looking at part C, now we need to look at the sum of forces in the y direction. So here we go. The sum of forces on our object in the y direction is equal to the mass of our object multiplied by its acceleration in the y direction. So we have two forces in the y direction, Fn, which is directed up, and Fg, which is directed down. I'm going to refer to Fn as positive because it's aligned with the positive y direction. So we'll have something that resembles this. Fn minus Fg is equal to the mass of our car multiplied by its acceleration. Now the car is moving in the x direction, it is slowing down, so there would be a horizontal acceleration. But we have to think about this in terms of the y direction, vertically. I think it's a safe assumption to assume that our car isn't moving vertically. It's not flying up off the ground, it's not sinking down into the ground, it's staying vertically stationary. It is moving horizontally, but not up or down. So by definition, is not accelerating if it is not moving. So our acceleration in the y direction will be 0. Mass times acceleration, well, any mass times 0 will just give us a value of 0. And now from here, I can simply add my force of gravity to the other side of my equation, add Fg over. And now we have an expression that can allow us to solve for the normal force. Fn is equal to our force of gravity. And we know, according to the equations that we've been dealing with, that our force of gravity is equal to the mass of our object multiplied by acceleration due to gravity for the planet that we're on, which here is the Earth. So, this is now getting us down to kind of parts D and parts E. Okay? We now need to solve for our force of gravity, which will then tell us our normal force. So here we go. Force of gravity is equal to mass times gravity. Excuse me. Our mass here was 2,200 kilograms. Acceleration due to gravity for the Earth, we can assume to be 9.81 meters per second squared. So we'll plug these values in. 2,200 multiplied by 9.81. That will give us a pretty large value for force, but But again, we have a large object that the Earth is pulling on. 21,582. And that is a force value, kilogram meters per second, so newtons. And remember, because of what we've determined with Newton's second law in the y direction, our normal force is equal to our force of gravity. That will not always be true, but it is true here because we have one force up, one force down, normal and gravity, and there's no acceleration, so by definition they would have to be equal. But again, that is only true because of the conditions we have here. So now that we know our normal force, we can then, I believe, come back to our equation for force of friction, F sub k. This is going to take us into part F. So here we go. F sub k is equal to our coefficient, mu sub k, which the problem statement tells us is 0.7. And then we're just going to take the normal force we just found, 21,582, and I'm going to plug that in here. So 0.7 multiplied by 21,582 newtons. So 0.7 times 21,582. I now get a value for my force of friction, F sub k, that is equal to 15,107.4 newtons. So now we have our force of friction. But remember, that's not exactly what we are trying to get to as our end goal. We want to know an acceleration value that will eventually help us with a kinematic equation to get delta x. So this is a really good start, right? But we're not quite finished. Just to recap, we drew a picture of our scenario. We looked at the forces acting on our object, our free body diagram. We looked at the forces in the x direction to see if we had enough information to find our force of friction. Figured out we did not. So we realized to find our force of friction, we needed the normal force. So we then looked at the forces in the y direction. We determined, using Newton's second law, that the normal force here was equal to our force of gravity. So we found that value, Fn, which was equal to Fg. We plugged Fn back in here to our equation for force of friction, and now we have our force of friction. So what I'm going to do now is I'm going to come all the way back to our sum of forces in the x direction, which we said equals mass times acceleration in the x. So what we found was that the only force we had in the x direction was our force of friction, which we said was negative because it was pointed to the left. So negative Fk equals mass times acceleration in the x. So if I want to find my acceleration, well, I need to divide my mass term over. So I'll divide by mass on both sides of my equation. Negative Fk over m, we can plug those values in. M over m, those will reduce down to 1. So now we'll have an expression that looks like this. Our acceleration in the x direction is equal to negative f sub k divided by m. And now, it's really just a matter of plugging in our variables. F sub k was, I believe, 15,107.4. There's a negative here, newtons, divided by our mass, 2,200 kilograms. So, take our values, negative 15,107.4 divided by 2,200, we get approximately negative 6.87. Now, our acceleration, because it is negative, means that our velocity is going to go down. It's going to go from a positive value, and our velocity is going to become more negative. We're going to go towards 0, which makes sense. Our car, upon realizing that our fluffy animals are in front of it, wants to brake so that it avoids hitting the animals. So now that we have our acceleration, this entire problem becomes a kinematics problem, okay? So what I'm going to do here is, just like with any kinematics problem, I'm going to list out my variables. Delta x, my initial velocity, which we were provided with, about 60 miles an hour or 26.8 meters per second. Final velocity, well think, we're not really told the final velocity here, but if we're coming to a stop, our final velocity should be stopped, arrested value, 0 meters per second. Acceleration we just determined to be negative 6.887, that's right. Wanted to say 89 meters per second squared. Time we're unsure about. And delta x is what we want to solve for. Now remember, we're not going to use 46 as our delta x. We're going to solve for delta x and see how that compares to 46. Right? Do we have enough space to stop? Or are we going to hit the animals? So if time is the variable that we don't know, that means we're going to use equation number 5. v1 squared is equal to v0 squared plus 2a delta x. v1 I already know is going to be 0, so 0 squared will still just be 0. So we'll plug in 0 is equal to our initial velocity, 26.8 meters per second squared plus 2 times negative 6.87 times delta x. So I'm just going to plug some values into my calculator. 26.8 squared is going to give us 0 is equal to 718.24 minus, because now we have 2 times negative 6.87. Oop. Mistake there. Minus 13.74 times delta x. Now from here, well, there's really 2 things we can do. We can either move over the 718.24 or we can move over the 13.74 delta x. Either one. I'm going to go ahead and move over the 13.74 so that my numbers will remain positive. So 13.74 delta x, 13.74 delta x, those will cancel out. And we'll be left with an expression that looks like this. 13.74 multiplied by delta x is equal to 718.24. And now, to get delta x by itself, we just need to divide by 13.74. Here we go. Divide by 13.74 on one side. We have to mirror that and do the same thing on the other side to make sure our equation stays equal. So delta x is now going to be 718.24 divided by 13.74. We'll plug this in. Okay. Looks like we end up getting a value of delta x of approximately 52.3. So what that tells us is that under these conditions, it would take our car 52.3 meters to stop. If we only have 46 meters in which to stop, that should tell us, unfortunately, there's going to be a collision between our car and our little fluffy animals. So, unfortunately, that does happen. So, my apologies. That's just how the problem went. But the idea here is we want to be able to see the connection between using Newton's laws of motion and forces in free body diagrams with our kinematic equations and how we understand why objects do the things that they do. So hopefully this gives us some direction on what we're doing with group problem number 4A. Remember, there is a key for the problem on Canvas if you want to go through and check your work there as well. Best of luck.